I think we can start. So hello everyone and good afternoon. I am Lapo Bracconi, and on behalf of ETA Florence Renewable Energies, technical organizer of this webinar, I welcome you to IEA Bioenergy's webinar series. Today's webinar is titled Integration of Gasification Processes in Biorefineries. The webinar will be moderated by Beren Vreugdenil, and it will feature presentation by Jitka Hrbec from the Institute of Chemical and Energy Engineering from the University of Natural Resources and Life Sciences in Vienna, in Austria, and by Johannes Lindorfer from the Energy Institute, Johannes Kepler University in Linz, also Austria. The authors of the report this webinar is based on are also present here and will be available to answer questions during the webinar. And they are Joachim Lundgren, who unfortunately is not at present here due to unforeseen circumstances, but may join later on during the webinar. Donatella Barisano and Enrico Catizzone from Enea in Italy. Rainer Rauch from Karlsruher Institute for Technology in Germany, and also Beren Vreugdenil from TNO, who is also an author of the report, on top of being our moderator today. During the webinar, you will be able to ask questions to the presenters and the authors of the report using the Q&A tab at the bottom of the Zoom window. You can also upvote questions asked by other attendees, and the questions who receive the most upvotes will be showed up higher in the Q&A tab. Due to time constraints, not all questions can be answered live, of course, but some questions can be answered in writing in the Q&A tab by the presenters and authors of the report. The report that this webinar is based on is already available on IEA Bioenergy's website, so make sure to check it out. And now, without further ado, I would like to yield the floor to Jitka Hrbec, our first presenter today, and I wish all of you a pleasant stay with us this afternoon. Jitka, the floor is yours.
Thank you very much for the introduction. Ladies and gentlemen, my name is Jitka Hrbec. I am a senior scientist at the University of Natural Resources and Life Sciences in Vienna. I am also an Austrian representative in the task and co-leader. And today I will start a presentation on integration of gasification processes in biorefineries. I hope you can see the presentation now.
Yes.
Is it fine?
Yes.
Okay. Okay, let's start. At the beginning, to outline of my presentation, I will start with a short introduction on the topic, then some words to gasification applications and a feedstock which is suitable for the gasification process. Then I will describe few gasification facilities, and we will come to case studies. The report we published in December last year has 4 different case studies how the gasification can be implemented in other technologies. So, at the end, I will make a short conclusions. So, as I told you, last year, we in the task published a report on gasification applications in existing infrastructures for production of sustainable value-added products. Here is the link at the bottom. Here can be find the publication included these 4 case studies, and the aim of the project was to show the great high potential of the gasification technology, also to mention the limiting factors for gasification, and last but not least to provide the data for third analysis which were carried out by task 42, which will be presented by Johannes today. Some words to gasification applications. On this figure, you can see a nice overview. We will start with at the best dry solid feedstock, but anyway, also wet feedstock is suitable for the gasification. After the gasification, we will get a producer gas, and after cleaning and conditioning, we will get a syngas. This syngas mostly is consisting of CO and hydrogen. And from this syngas, it is possible to make several products. gaseous products on the left-hand side, you can see SNG, hydrogen, ammonia, and liquid products, Fischer-Tropsch fuels, mixed alcohols, methanol or DME. And syngas can be used also for the production of heat, for combined heat and power, high temperature heat, or in co-firing. Some words to potential of gasification. Gasification is a great technology because a variety of feedstock can be used. It is not just a clean biomass for the gasification suitable, but also residues and waste materials can be employed. The process can be performed by diverse operational conditions using different gasification reactors. And as I already told, many different products can be made in this way. Gasification can be implemented as a standalone technology, or it can be a synergy on implementation with other industrial processes. Something to feedstock, which is suitable for the gasification. Here is an overview. There are three main categories. It's woody biomass and waste, agricultural residues, and residential and industrial waste streams. And if you look at the right side, there is a table which was published by VBA. It's a World Bioenergy Association, and you can see the potential of the biomass or residues. I have to point it out that in the table, no residential and industrial waste are mentioned. It means the potential is even higher. So if you look at the potential in year 2035, you have here 150 exajoules. So, and for the comparison, the power consumption in Germany in 2021 was about 2.1 exajoules. So the potential is really, really high. So the feedstock, in the report, there is some limiting factors described, which should be mentioned if we are talking about gasification. For the gasification process, the feedstock must be adjusted. It means the size and the impurities must be removed, and feedstock must be adjustment for the further processing. Important is also the feedstock moisture, which has a strong effect on the process efficiency, and also a chemical composition of the feedstock. Carbon, nitrogen, sulfur, chlorine, alkali metals, and trace elements are very important for the right gasification process because they influence the further products. Byproduct stars, heating value of the gas, and the ash content and melting behavior. So if the feedstock consists a lot of chlor or alkali metals, so you have a problem with the melting temperature. Here is an overview on gasification facilities, which are mentioned also in the report. We didn't mention plasma gasification. We described just the classical gasification reactors. It's a fixed bed gasifier, fluidized bed, and entrained flow gasifier. And now we are coming to case studies. Case studies, it's the main focus of the whole report because we wanted to show that the gasification can be implemented in other technological processes to boost the production or to make a high efficiency. So these case studies are case study 1 on entrained flow biomass gasification in the pulp and paper industry. The author was Joachim Lundgren. He is unfortunately not available today, but anyway, he will be able to answer the questions per email. The second study was on integration between gasification and anaerobic digestion to production of methanol by Donatella and her colleague. And the third case study was made by Reinhard Rauch. The topic was integration of renewables into existing refineries. And the fourth case study by Bear and Vreugdenhil, gasification of RDF and integration into an existing naphtha cracker. So the case study number 1, entrain flow biomass gasification in the pulp and paper industry. As an introduction, I have to point it out that the pulp and paper plants are really highly suitable for the integration of biorefinery concepts and for the gasification, thermal gasification-based concepts, and byproducts can be used in the process. The product gas can be used for high temperature heat for the companies, for the process itself, or it can be upgraded in more advanced applications like biofuels or biochemicals, and as well for drying purposes, which are needed for several technological processes. So what are the benefits of integration of gasification in pulp and paper industries? It's an efficient heat integration. So as I said already, high temperature heat, for example. The investment costs are reduced because there is a co-use and synergy of existing processes and equipment. And also there is also experience of feedstock and handling and the processing and utilization. Here are several examples of integrated gasification units into pulp mills. The most of them are in Scandinavian countries, but also in China, Indonesia, and mostly they replace the heavy fuel oil, or they are used for high temperature heat in the process, and so on. We have also some other examples. For example, in the Netherlands, we have a ESCA graphic board company which converts paper reject into gas via gasification in 2 megawatt air-blown CFB gasifier, and the product gas is combusted and used for steam production. And we have also the news that there is a Andritz group which received an order to build in Brazil a gasifier. It should be a 51 megawatt gasification plant together with belt dryer. So it should be built in mill in Ortigueira. And in this case study made by Joachim, there were 2 options considered. So if we want to integrate the gasification process into the pulp and paper industry, so we have the possibility to replace the bark boiler of pulp mill with entrained flow biomass gasifier, or the second pathway was a full or partial utilization of the black liquor stream for entrained flow gasification. And 2 results. Unfortunately, we have not really time enough that I can describe the case studies in detail. But anyway, here are the most important conclusions. So I would like to invite you to visit our website and to check the details for each case study. So to conclusions, Joachim concluded that favorable conditions for biofuels and chemicals production are better in kraft pulp mills due to the already available feedstock and woody residues, and black liquor, which is really fine for efficient heat integration. The overall energy system efficiency is generally higher and the performance is better if it's integrated in a pulp mill instead of to make a standalone operation of the mill. The pulp mill characteristics as a capacity, it is decisive for what integration concept is the most favorable from economical point of view. And gasification with downstream synthesis to biofuels and biochemicals is limited in the lime kiln to due to increased causing load. And the gasification of black liquor with downstream synthesis processes results in good economic and energy performance. So it's really supported for this process. So this was the case study number 1. And now we have the case study number 2. The authors are Donatella Barisano and Enrico Cavizone. The topic was gasification for production of biomethanol by coupling with anaerobic digestion. And what were the drivers for this study? It was that methanol has a large employment and it's a key chemical as alone, or it's an intermediate as well. The anaerobic digestion is an improved technology since many years, and based on many scenarios, the potential is still increasing. So we can see more and more biogas stations over the world. And the coupling of thermochemical gasification with anaerobic digestion was chosen to boost the production of biomethanol. Also here, 2 subcases were considered in this case study. The first one was the production of biomethanol by enriching the producer gas from biomass gasification in hydrogen via steam reforming from IEA biomethane plant. And the second case was the anaerobic digestate, which was used as a feedstock for the gasification process. How did Donatella and her colleagues made? So something to materials and methods. In subcase 1, the gasification unit was based on steam oxygen gasification process. It was a bubbling fluidized bed and the temperature was between 820 and 880 degrees. It was coupled with filter and scrubber. And in subcase 2, here was the rotary kiln reactor chosen. Air was used as a gasification agent, and the process was carried out by a temperature between 800 and 830 degrees C. In the table, you can see a composition of the syngas stream. In the case 1, almond shells were used as a feedstock, and in the second case, it was a digestate from IEA plant. So something to result in case 1. In this case, the producer gas from biomass was enriched from hydrogen from IEA plant. The biomass flow rate strongly affected the syngas composition for the methanol synthesis and the specific power consumption. And it should be said that despite the increase of syngas to be compressed, the increase of biomass flow rate caused a slight decrease on electricity. The effect is related to the total methanol productivity. And in case 2, in this case, the digestate was used as a feedstock for the gasification, and it seems to be a promising way for producing methanol, and the productivity of methanol is slightly lower in this case. It is better in case 1, so in subcase 1, and this Donatella thought this may be associated to a different syngas composition. In fact, it provides a possible alternative to use this digestate as a feedstock for the gasification if there is enough of this. Otherwise, it is also used as an agriculture soil improver. So it was the case study 2, and now we have a case study 3. This case study was made by Reinhard Rauch and his colleague. The topic was integration of renewables into existing refineries, and it was the way how the renewables can substitute the fossil fuels in the refineries. The aim of the study was to show the complete synthesis pathway of the biofuels. It was studied on site in one of Germany's largest refinery, Mineralölraffinerie Oberhain. The abbreviation is MIRO. So you can see here a block diagram of main refinery structures at the MIRO refinery. So you can see the blue one, distillation steps, then red one, conversion, yellow, desulfurization, and gray, upgrading. As you can see at the beginning, you have a crude oil, and at the end, you have several different products. Also, in this case study, two different pathways were compared. There was a sub-case 1. It was focused on Fischer-Tropsch process. This Fischer-Tropsch process is more adequate for synthesis of high-quality diesel. In the sub-case 2, it was methanol DME to gasoline, and in this sub-case, it was focusing on high-quality gasoline components. So here you can see a block diagram of the integration of the gasification system. It was a sub-case 1, Fischer-Tropsch process. So if you can see, you can start with staged gasification. Of the first stage is a pyrolysis, then the biocrude is fed into the entrained flow gasifier, and after water gas shift, you can come to Fischer-Tropsch synthesis, and this syn crude will be then sent to refinery for further processing. Something to materials and methods. The yield target of 50 tons per hour was feed was mentioned to send to refinery system, and it was set for the evaluation process. And also the efficiency of the process was analyzed through the energy efficiency factors, where the energy of synthetic fuel byproducts and overall steam and fuel skid production were compared to the energy of biomass feedstock. We have here these two sub-cases. The Fischer-Tropsch raw product, it can be treated in a refinery as a synthetic crude oil in a similar way and fed to the conventional crude oil into atmospheric distillation unit. Then it is processed in the refinery structures, and the main end product is expected to be diesel with byproducts as gasoline and light hydrocarbons. The second case, MTG and D2G processes produce a raw product. It, as I already told you, it's focusing on gasoline. It is comparable in the quality and composition to the reformate of the catalytic reformer in the refinery. And this is the description of the gasifier, which was mentioned in the study. Maybe the most of you know already the Biorefining process, which is at KIT in Germany. So it's a two-step process. It's fast. The first is the fast pyrolysis process, where the biosyncrude is produced, and this biosyncrude is fed into the high-pressure entrained flow gasification unit. And after the gas cleaning and conditioning, you have also a catalysis, and you can make a DME synthesis and other synfuels productions. The conditions, the temperature by the pyrolysis is about 500 degrees C. Gasification part is over 1000, it's 1200 degrees C. And the raw synthesis gas contains mainly hydrogen, carbon monoxide, carbon dioxide, and steam. And something to results of this case study 3. The Fischer-Tropsch process with the implementation of hydrocracker unit was shown to produce higher yield of diesel components compared to catalytic cracking and higher overall efficiency. Methanol or DME to gasoline processes deliver lower synthetic fuel energy compared to Fischer-Tropsch process. And amongst the methanol to gasoline and DME to gasoline process, D2G process could deliver a higher yield of synthetic gasoline. So also a higher synthetic fuel energy efficiency compared to M2G process can be reached. The integration of the Fischer-Tropsch process resulted to be slightly more economic compared to methanol or DME to gasoline process. So it was the case study 3, and now the last case study, which was written by Berend and his colleague. The topic was gasification of RDF and integration into an existing naphtha cracker. So you can see here the overall picture. And the aim of the project was to employ gasification technology to provide circular and bio-based feedstock to an existing naphtha cracker of petrochemical plant. So in this case, the Milena gasification, Olga tar removal facility, and absorption enhanced water gas shift reactor were used in this case study. Some words to Milena gasifier, you can see it in the figure here. So the feedstock is fed to the reactor from the bottom. It's RDF, it's a mixture, it's a biogenic part and also a fossil part, so it's a plastic. And it is gasified here, and there are already two different parts. There's a gasification part, it's here, and here is the combustion part. The heat from the combustion part can be given to the gasification part. So in this reactor, no circulation of solids are needed. And the bottom of the riser can be fluidized using steam or nitrogen or several other gases. So it's flexible. And Berend also mentioned in his case studies the comparison of gas produced by RDF gasification and CO2 removal. And he compared it to the gas from naphtha cracker. So you can see RDF here in blue and naphtha gas in orange. So here is the setting for mass and energy balance, which was made by Berend. So you will start with the gasification in Milena, then you have a tar removal, and then you have absorption enhanced water gas shift reaction. And the conclusions: operating existing naphtha crackers on alternative fuels is typically looking at replacing naphtha and fossil fuels with a biogenic or circular, it means mixed waste alternatives, and to maintain 100% recycling efficiency for the plastic, a certain amount of biogenic residues is crucial for the process. Anyway, it's also a benefit that no detailed recycling is necessary. And very important will be the policy frames for this process and for the development in this field. The focus is to generate as much as circular materials from waste, and the gasification route needs to be supported with CO2 mechanism favoring the sequestration of biogenic carbon. And some words to conclusions. So if we have written this report, so we wanted to highlight that the gasification is a versatile technology because several feedstock can be used in this way. It's not just the clean wood, it's also waste and residues, agriculture or forestry residues, or even municipal solid waste or industrial waste streams and so on. The process conditions are also variable, so you can use several temperatures, several oxidating agents, several reactors as you like. And also you can produce many different products, liquid biofuels or gaseous biofuels or biochemicals. You can make a bioenergy from that. And it's also good to integrate the gasification process into other industrial processes And last but not least, we have to mention that gasification is very suitable technology for carbon capture, utilization and storage of the carbon. So in these 4 case studies, we illustrated partly the potential of the gasification technology. It's clear that there are more case studies which were not included in the report. But anyway, we included these 4 different case studies to illustrate the potential. It was employment in pulp and paper industry, methanol production, coupling with AD plants, integration of renewables in existing refineries, and RDF gasification and integration into naphtha cracker. And the message from this presentation should be that gasification processes offer a wide application in the field of bioeconomy or biorefinery concepts to utilize residue and waste streams. So it means circular economy. And this increase the overall efficiency of conversion process and also optimize the materials and utilization. So, and that's all from my side. I thank you for your attention and give over to Berend.
Thank you, Jitka. Yes, there's quite a few questions in the chat which are being answered at the moment by Reinhard, and also I answered some questions myself. But maybe to you, Jitka, the first 2 questions you might be able to answer. The first by Loic Leclerc is the potential, the actual mobilizable potential, or the theoretical? Meaning, is some of the feedstock already claimed by other processes? So that was about the feedstock availability that you showed.
Yes, it was a feedstock availability, and it was a theoretical potential of the feedstock. So it was it's clear that the feedstock can be used in also other different ways, not just for the gasification. So it was a theoretical overview.
Yeah, I think that's in general the case with most feedstocks, that it's often they are utilized in other ways, but not per se the best form. And the second, maybe you have an answer to that, by Ayush Agarwal. Which analytical tools and techniques you use to measure trace elements in the feedstock? And what is the order of magnitude of the concentrations of the analytes, ppm, ppb, or something else?
So for this, we have a special analyzer for the metals and for other. So I think it's equipment of each laboratory. So we have no special techniques for that.
No, yeah, I think the trace elements you can typically find to ppm, depending on the elements, also to ppb level, but it really depends indeed on what type of analysis department analyze you have, how well equipped.
Yes, but it's mostly the problem, because in the most of the feedstock, these elements are in really low concentrations, so it's not possible maybe to catch all of them. So, but the most of them.
Yeah. Okay, then I suggest to continue now with the presentation of Johannes. In the meantime, I think my colleagues will continue answering some of the questions in the chat. And at the end of the presentation of Johannes, there's room for some more questions. Thank you, Jitka. And Johannes, the floor is yours.
Yeah, warm good afternoon. My name is Johannes Lindhofer. I'm working for the Energy Institute at the Johannes Kepler University in Linz, Austria. I will follow up on the presentation of Jitka with the topic Technical, Economic and Environmental Assessment of Integrated Biorefineries based on the gasification technology. I will go through a short introduction of the IEA Bioenergy Task 42, where I work for, or where I'm kind of representing today. The TEE methodology itself, where we are looking at the technical, economic, and environmental impacts of certain biorefinery cases and case studies. And then I dive into selected case studies that we took from the previous presented ones. There is always on those case studies a part A, which deals with the basic technical characterization within that TEE assessment method. And then it's about the quantitative characterization to really compile very basic environmental and economic indicators. Finally, conclusions and lessons learned will be presented. So at the moment, it's quite clear, and probably to this auditorium even clearer, that there is really a perfect momentum for a sustainable recovery. You see here really the huge increase of import prices of mineral oil and natural gas. It is a European representative illustration. Over the last month, it really went up tremendously. At the same time, also the derivatives like jet fuel prices really absolutely accelerated, and the same for CO2 emission allowances, which are displayed here. So we feel that there is for sure a strong driver, especially by the European Commission with its Fit for 55 package at the moment, where the EU ETS schematic is a really major decarbonization tool. But so the enablers like biorefineries are for that transition towards renewables, for that transition towards a circular economy really can take off at the moment. And the strong candidates for this have been presented also by Jitka. So we see on the biorefinery in general, really that there are a lot of technological solutions out there and under development. The challenge is really here in that sector to appropriately implement and potentially also combine them as presented by the case studies by Jitka. Concerning the IEA Task 42, it's a collaboration that really is targeting the sustainable processing of biomass into a portfolio of marketable bio-based products. So looking at the chemicals, the materials, the minerals, and the bioenergy as additional, as a so-called, as a full integrated schematic and technological options there. There has been quite a lot of output, so I really encourage you and all the participants here to visit our website, task42bioenergy.com, and go for the different outputs, reports, published newsletters. There are country reports on the status of the biorefineries to really kind of facilitate commercialization, market deployment, and the various aspects that are related to that. And one topic where I'm involved in or working on is on this so-called TEE assessment. So it's a quantitative, environmental, and economic assessment approach. We are generating generic, very basic initial biorefinery models that some sort of can act as a baseline, as a showcase. And then we're also trying to encourage stakeholders for that technology evaluation, because it is quite a complex topic and you need a lot of knowledge to really get the right numbers in place for that evaluation. So that's why we are quite happy for that cooperation also with Task 33, where the experts on gasification are, and then we can kind of take their case studies and build it into that schematic and modeling. What has been the output also on task 42, or what is relevant for that assessment that I'm presenting here, is also this polyhierarchical classification system in order to establish a common language on bio-based and multi-feedstock and multi-product systems, which are biorefineries basically. So starting from the raw material, having different processes, and then generating platforms where you then further on convert them to always a material product, an energy product, and partially or sometimes also co-products. So the idea is to condense very complex technical systems towards a very simplified schematic illustration. What is the TEE assessment about? So the idea is to follow a stringent approach and principle via defining key case study characteristics at the beginning of the assessment. So what is the system boundary? What is the basic flow chart? How does the process look like in a very simplified schematic? Then filling this with quantitative numbers in terms of what is the input and the output balance of the bio-based system, and then compare it to a reference system, which is at the moment basically a fossil-based one. When you have all the key characteristics for that, put it together in the schematic that you need, then you can go to the value chain assessment, what we call a value chain sustainability assessment, where it's all about the environmental impacts, going for rather very basic indicators, like very common ones as global warming potential, and then deriving CO2 savings compared to the benchmark for the specific, in that case, gasification-based biorefinery setup. Other indicators that we have included here at the moment are, for example, the cumulated fossil energy demand. So what is the primary energy demand in terms of renewable input, but also fossil inputs? And others are more related to efficiency. So what is the carbon to product indicator? What about fuel efficiency conversion from feedstock towards carbon in the product portfolio? The economic indicators are the other pillars of sustainability assessment. And there it's really a very, very simplified comparison between like cost and revenues for a schematic setup of a biorefinery case. So scaling a certain plant at a certain place at a certain time, and then calculating estimated values in terms of what are the costs and the revenues. We can also deal or focus on specific production costs or a bit more elaborated indicators like the net present value. So that's just a bit of a deeper dive into what are the methods and tools that we apply and instruments for the financial impact estimates. The whole story is also based on a norm. It's the VDI 6310. And the net present value is a nice economic indicator that we go for if we have the data available. So CAPEX, it's quite straightforward. We consider depreciation effects over a lifetime of 10 years in the case studies that I'm presenting now, and the interest rate of 5% operating hours per year, full time, so 8,600 hours per year. The OPEX are comprising the main raw materials, additional operating expenses, and maintenance. So very common procedure for the financial impact in terms of environmental impact estimates. So we are also not claiming a full LCA in that respect. but we are looking at the systems with specific emission indicators and emission factors, also considering the upstream. So it is some sort of partly aligned with current legislations like the calculation methodology in the European Renewable Energy Directive, or also in the US, the Renewable Fuel Standard, but it's probably a bit condensed compared to a full life cycle assessment. We really try to avoid the very complex allocation. For all of those who have ever done life cycle assessment, it's quite complex. For a biorefinery, if you have these versatile products, you have to split the impacts between the different products. And with the approach that we choose, we are really avoiding this in order to extend the system boundary to this whole biorefinery setup and plant. So when this all has been then done and put together, we are compiling so-called accumulate the data to so-called fact sheets that follow this description, or that appearance that I've already described. I would like now to really go into this practical procedure, how the things are compiled. So at the beginning, we are starting really on a very high flight level in terms of the this example illustration. What are the main parts of the technology that we're looking at? Then we go for the system boundaries. So normally it's cradle to gate, that where our case studies are situated at, because we know, okay, the biomass-based feedstock, so biomass cultivation, and then to the standardized gasification-based fuels, and also energy carriers, additional energy carriers there. What is quite relevant is the development status. So if we have data, or if we're yielding data from a simulation, or whether we have data from real-world proof implementations in industrial environment, that totally puts another spotlight on the value of that data. So this is quite relevant to be distinguished between. And then it's about the data mining. So going step by step through the processes and compiling the mass and energy balances of the unit operations, and then summing it up to an overall figure, basically, along the value chain. And with that kind of introduction on how this is done, I'm diving into some case studies where parts have been already also presented by Jitka. I'm focusing on the case studies of number 3 that she was presenting. So the first one is about the Fischer-Tropsch process for high quality diesel. Here is the sketch that I've taken from that publication. So the modeling that has been done there was strongly focusing on the implementation of into the refinery system, as Jitka was mentioning, and we basically then kind of put it additionally on to this, the whole feedstock provision and the gasification itself. And this is then the translation of the technical simulation analysis towards that method, towards that part A that is looking at the case study. And so we have here a 3-platform biorefinery with a biocrude, synthesis gas, electricity, and heat as the platforms, using wood biomass as a feedstock for the production of Fischer-Tropsch diesel, Fischer-Tropsch gasoline, refinery gas, propylene, electricity, and heat via entrained flow gasification and Fischer-Tropsch synthesis. The next part is on the data. So the really relevant mass inputs and outputs are here displayed for the 2 variants, for a catalytic cracker and a hydrocracker. And what is quite relevant for sure for that assessment that we do are the efficiencies that are reported. And what also is probably relevant, that we normalize such a case to a certain level of output, to a certain, we can call it scaling. Here it is 100,000 tons of synthetic fuel per annum. So combining gasoline and diesel for that case. The next part is about illustrating this normalized mass and energy balance. So for the looking at the mass balance, comparing input and output for the various fractions, the major various fractions, the very simplified energy balance is displayed here, where for sure the strong demand is from the biomass feedstock. And those are the two. So the two graphs on the upper side are related to the FCC system, and the lower ones are pretty much comparable, but for the FTHG modeling. You see slightly differences in the product portfolio that are displayed here, but the aggregation level is a very high one. So it is really summed up with that method. Going to the next part of that assessment, we are at the cost structure, summing up operational expenditures and capital expenditures for the two specific case studies are illustrated here. We see that the operational expenditures have a higher proportion on the specific product cost than the capital expenditures in that assessment. It is quite clear or known by all of you or everybody who has ever kind of compiled such studies, techno-economic studies, or written those or read about it, that all in all, it's absolutely relevant what are the basic assumptions behind that. And our approach is really to strongly display what is the basic assumption and to kind of go out with that in order to also discuss and refine it, because for sure it's a very static approach. And as I've shown in the second slide, highly fluctuating prices can definitely not be fully reflected with that static approach. But for sure, for that, you can add on additional sensitivity analysis, and you get a first feeling and impression what might be beneficial, where are the points to turn, where are the influential hotspots for the assessment. Coming from the economics towards the environmental impacts, we are comparing the biomass-based system, so the biorefinery setup, with a fossil-based system to generate equality in terms of the service capacity of the technology and the outputs. When we compare that, it is absolutely tremendously visible that especially for the greenhouse gas emissions and also for the primary energy demand, the biorefinery setup is, especially for the energy, close to energy self-sustaining, or basically designed to energy self-sustain. And therefore the emissions are enormously low. And so these integrations are enormously beneficial in terms of GHG savings. So these are highly significant. In terms of the primary energy demand, we see that when we compare the biomass input versus the end products, that there for sure is a strong increase in energy density. So you need a bit more, you need significant more input because also of, for sure, the conversion efficiency. But the idea is really to be comparable and to be transparent on that side. Concerning the cost and revenue comparison, as I said, it's tremendously relevant. What are the basic revenues anticipated for the specific products? And there are a lot of, let's say, tipping points to generate business cases at the moment. So CO2 emission certificates can really leverage additional incomes for the specific cases, and also very small increases in revenues as anticipated in that sentence can completely change the picture in the net present value calculation. So what we really see that this expansion of the material product portfolio can absolutely bring additional value creation for different products. So here you see propylene, as this is different for that scale, for that setup, but also additional options are waste heat utilization for additional marketable products for the setup. So I will dive a bit faster to the other cases in order to save a bit time, because it's a bit replicatory. Again, this is the schematic, how we went to the methanol DMA process for gasoline blend. The difference is not that big in the representation. Also, in that case, we took the same reference flow for the 100,000 tons per year. And then here again, the input in terms of biomass and oxygen and the output are compared in a very simplified mass balance. And on the right-hand side, you see the energy balance for that case. Same done for the cost structures and the revenue structures. Go for that, and also for the greenhouse gas emission calculations. Enormous savings on that side, and those are the real tangible and strong benefits for an implementation when we roll out such a technology. So this again is a comparison on the primary energy demand. We see this rather high biomass uptake for providing the product energy content, but also the energy provision within the conversion process. And with that, I dive into my last case study that I've prepared for today. It's on the methanol pathway, methanol to gasoline, and the gasoline blend. Again, the reference flow are the 100,000. So changes are normally, especially on the efficiency side and for sure on the product side. Here it is illustrated in the same representation. Again, the generation of the product portfolio is very versatile for that setup, and we have implemented specific cost structures and revenue structures for those products to compare them and to calculate the CAPEX and OPEX for that. And we see really this strong influence on the process economics by the price for sure, and that's also for the availability for the feedstock and raw material. So here we have quite conservative assumptions in terms of that we use very standardized woody biomass feedstock with approximately 80 euros per ton dry matter. That's a rather high cost. So low cost feedstocks will generate favorable economic results also on that sketch and that representation. Again, the savings are really significant. We can really reach enormous greenhouse gas savings and positive substitutions for fossil fuel consumption with a relevant implementation of such a case. So I will go quite fast through those slides, but what I would still want to point out, if we look at such a case, also the main fuel product is really decisive. So when we think here, or when we have a look at the synthetic gasoline, which is the blue bar, then okay, for sure it's the main mass proportion that is outputted from such a plant, from such an implementation. Therefore, it's really essential to yield a significant price for that main product. And here also the obligation is from the public and political instruments to seed a reasonable pricing and to enable therefore also additional implementations of such technologies, because you have a very broad product portfolio, but the revenues for the main product that are reasonable and that can bring an economic life towards such implementations is really relevant and essential. So there are a lot of variables on that, but current subsidies and the legal framework conditions for advanced biofuels are really sensitive. That's not just for Europe. I'm pretty sure that's for the whole world, for that assessments. So I'm trying to bring some lessons learned for the case studies. We have done also a stakeholder consultation by an extensive survey on the topic. And we really saw, okay, it is quite complex to get data from people working in the field, because there are a lot of restrictions on the quantitative data. So you can imagine somebody asking for economic revenues for a certain technology implementation, it's rather problematic. At the moment, we are more focusing from the environmental perspective on primary energy demand and global warming potential, as they are the most prominent one, but also other parameters like land use need and so on should be considered in future applications. For that all, there is not a real standard and operating procedure to look at technical, economic, and environmental schematics of such implementations, but they are definitely all equally relevant. So that approach can definitely bring value to schematically illustrate the benefits. It's quite essential to conduct uncertainty analysis due to that insecurity of input parameters and variables, especially with the economics. So the physics in terms of mass and energy balances are quite settled. So environmental impacts are, let's take it like that, more easily and classically to be quantified. From the technical perspective, it is really relevant to have a high overall efficiency on the feedstock valorization. We compared the results of the case study with other literature, and especially the flexible fuel gasifier with high feedstock flexibility and low requirements for raw material quality with a very high efficiency is an absolutely favorable concept that can really pave the way as a technology for the decarbonization of the transport sectors, but also for other base chemical sectors like plastics, as Jitka also highlighted. So what are the environmental conclusions on our work here? The main focus is really here to showcase significant carbon dioxide and global warming reductions, because these are the real drivers for those technologies. And we calculated this with factor-based calculations, but considering also upstream emissions. So still quite a concise option and method. We avoided allocation procedures because we really looked at the multi-product systems and compared it with the fossil reference system, not just taking the single fuel, but also probably the chemical product into consideration. And the results are quite astonishing, or probably not astonishing, but quite promising, because the CO2 saving potentials in all the compared studies are above 90%, which is a really high one. So what is decisive for that is the input in terms of process energy. So an integrated setup where you have the renewable energy supply in the plant, in the setup, might lead to a bit higher primary energy consumption, but is really needed for a comprehensive sustainability claim. And for sure, with all the different technologies and options going for comparable or for the same feedstocks, stringent sustainability criteria are quite relevant. For the economic considerations, there are definitely just a few high TRL projects and plants in operation. So quite a little information on economic data has been published. There are a lot of TA assessments and so on, but TRL 9 and full operation is probably something that we would go for and that we would like to incorporate. We feel that specific production costs, so euro per ton of fuel or euro per megawatt hour of the energy carrier based on the higher heating value, is very common and relevant, but also this overall balancing of reference plants in case studies appears really to be equally adequate, because we do not need to split the efforts in terms of CapEx and OpEx between the different products, right? So we can really go for a full setup. It is quite clear that full load operating hours, the time horizon, and the scaling are really very relevant for an economic performance assessment. And what we've also seen, okay, these refineries are really huge. This is a huge amount of feedstock required, and they require significant investments. But all in all, also this, or especially the OpEx optimization in the sense of favorable feedstocks and sourcing is really relevant for being fully economic and generating a nice and representative business cases. And the current price increases that we see in the last couple of months are really potential tipping points to generate business cases for gasification-based biorefineries that have been probably not in place in the last 10 to 15 years. The method itself, it's dedicated for early design stages of technological implementation to really derive recommendations. Where are the hotspots in terms of economics, in terms of, okay, probably also efficiencies from the technical perspective, but also from the environmental perspective. And we have this modular approach that every unit operation has its own data set, and so it's also can potentially be combined to find the right opportunities towards a sustainable process setup. So to sum up, with that, I'm done with my presentation. You might think, okay, where can I read about it? We are actually finalizing a report on these case studies, and it's to be published this summer. So please stay in contact and look for it when it's published. And well, there are some other references on the topic where we evolved the method. So with that, thank you very much for your kind listening, and well, input and questions are always welcome. Thanks a lot.
Thank you, Johannes. It's a nice overview of how LCA work and support, well, basically what we're doing with gasification. There's still some questions left in the chat, and I don't think we have answers to all of them. But I would like to invite the other authors and Donatella, the other speaker, on stage. Maybe we can go through them. We still have some time left. We start with the first one by Butaina Ali, who asked, and I think maybe Johannes, you have an idea on this. What is the best way to enhance the efficiency of integrated biorefineries?
Yeah, I think in my personal point of view, there are different ways in terms of interpreting efficiency. So from the technical perspective, you have already interpreted it, or you have very kind of common formulations in terms of carbon to product efficiency, right? So coming from the feedstock and transferring as much as possible towards standardized and marketable products. But there is also this part of the economic efficiency where we see that going for higher hydrocarbons is really a worthy option in terms of that you really try to go for what always called as, let's say, the low volume but high value market uptakes. So very specific hydrocarbons with a huge market price or with a significant increased market price in terms of applications like C4 to C8 fractions, the various of them, instead of, for example, SNG substitutes, so going for a natural gas substitute. So just as a very brief option in the efficiency and so the various aspects in terms of economic efficiencies and technical efficiencies. Yeah. I was not really reading the chat, to be honest, during my presentation.
No, that's what I'm here for. But
not multitasking enough.
One of the other questions, and I think this is a complex one, by Genesis Aja. My laboratory designed an RDF gasification plant whose output is coupled to a modified diesel generator. Tests actually proved more than 60% reduction in diesel consumption of the generator, but the cost associated with obtaining and processing feedstock is high across the process chain. Is it sustainable over time such that it begins to pay back? I think the reason why this is so high is that you're building a whole lineup for a relatively small application. So if you connect a gasifier to a diesel generator, I don't think it's a very large application of your gasifier, but so your OPEX and your CAPEX compared to the output product will be very high, making it, well, economically not very sustainable. So in that sense, it's probably better to do something else or on a larger scale, to look for solutions on a larger scale. And that's my if one of the presenters has a different view, they can type that, but I think that's the reason. Ralon Hunt asks, I understand that the regulations in EU indicate that new liquid fuel production is required to have its own power source, which must be renewable to ensure a low carbon intensity score. How does intermittent renewable power match with the power needs of a refinery? That's a complex question. I think how does it match? I think talking from the gasification perspective, there's always a lot of options to include intermittent power. So to absorb basically a surplus in power production at moments when there's a lot of sun or wind available. And I think that's for biorefineries the same. So I think there's a lot of opportunities there to level out the peaks that are created by renewable power. Paolo Castelli asks, I do understand the greenhouse gas emission is considered as environmental impact, but when we will scale up and implement other emissions may require additional treatment, and social impact will be important in such respect for the success and cost of implementation. When is the time to consider these other emissions related to a certain technology like gasification? And then later on he says, I'm talking about environmental risk for malfunctioning, emissions during transients, etc., etc. Is that something you could answer, Johannes?
Well, it's quite clear that this is a shortcut approach that we are doing here. And if you're looking at the full life cycle perspective, you have a bunch of indicators that you should look at. And that is also probably what what we learned from the first generation versus second generation, also biofuels discussion, that we need to go for stringent sustainability criteria. Otherwise, we are transforming from one environmental indicator to another. So, for example, CO2 emissions towards land use change or whatever. But I think the approach that has been presented today, that there is a focus also on refuse-derived fuels, on alternative feedstock that has been characterized, gives the window of opportunity to overcome those problems. And if you are going for then a specific technical implementation, you will need specific technical clearances that are also environmentally, that are covering also environmental impacts from the local perspective. So we need to go for that global LCA perspective and for that local implementation perspective. And if that matches, I'm pretty convinced that we can overcome these constraints and also threats that are related to that.
Yeah. Okay, thank you. There's two questions which I think are in line. So it's Rabi Kabir Ahmad who asked, given the environmental degradation of infectious diseases are now a matter of life and death in many parts of the world as a result of the improper disposal of plastic waste, what are your thoughts on using plastic as feedstock for gasification processes in biorefineries to address these issues? I'm not completely sure what these issues are. And then the bottom question is, what about waste gasification to electricity to hydrogen? Well, I will try to give my perspective on utilizing waste, and this might be a personal perspective, so it depends on who you talk to. But I think in general, waste containing plastics will need to be recycled as much as possible, because we produce a lot of plastics from fossil resources, and we need to reduce the amount of fossil resources we use for that. So reusing plastics and also recycling them, and in the end also via gasification, recycling them is then the way to go. At some point, the degradation of the plastics or the quality of the feedstocks containing plastics is such that you cannot do a lot more than either gasifying it or burning it even to produce electricity and power. But that's then really the last resort. Using these feedstocks to go to hydrogen or electricity, I think is really a waste of carbon. So we have to focus on keeping carbon in the loop and supplementing with bio as much as possible, and try to avoid using these valuable feedstocks for production of electricity and hydrogen. I know it's possible, and I also know that there are companies doing this actually, but I think in the future it will move more towards reusing the plastics to make new plastics. Then there's also a question which, yeah, is I think by Vincenzo Nardi, which I think is a difficult one. Is the current economic environment with the war in the Ukraine, energy price spikes, etc., encouraging investors? I don't know who has a good view on that. I think it's maybe not an encouraging topic, but I think these changes do show the need for alternative solutions. And I see that Reinhard is coming online.
I think here you can add that normally investors would like to have a payback, to have a depreciation period of about 10 years. And these peaks are always very short, and hopefully also the war will be not 10 years, but shorter. So therefore, I think it will not influence investors, because it's always some peaks, and it's not a guarantee for a long time.
Yeah. Then there's a question by Siukri Manur. I think for Johannes, and I would like to add one question there as well in relation to the Ukraine topic. He asked, is the TE assessment received international recognition as a bioenergy certification activity? And my question to you, Johannes, is in your calculations, looking into the prices of the products or the value of the products, did you consider the pre-Ukraine, the pre-war prices, or and I think it would significantly improve if you look at the prices now. Is that true?
Yeah, absolutely true. Thank you for that additional comment. So if you probably look then in the slides, I didn't really point it out to the maximum extent, but these are the evaluations has been done a couple of months ago. So the current extreme increase, so at least we would see 30% increase, especially for the pricing situation, is not considered in these evaluations, to be clear on that. And that would definitely favor like more positive net present value representations, or like more positive revenues on the cases for the biorefinery setups, and not too much increased feedstock prices. So that did not kind of take off in the same level that I've looked before, to be a bit prepared for that, to be honest. And the other part was it's certification. So it is some sort of a homemade method, to really frankly speaking, that combines different methods that are recognized. So you basically would be able to take parts of it to then go, for example, an environmental footprint certification or things like that. So the basic idea is within the normative framework that is out there for the bioplastics, also for the biofuels on the international level, but it is a bit, let's say, downsized and shortcutted. So we would need to extend the documentation and the referencing for that.
Okay, thanks. Then there's a question by Gabo Talero, who asked, what can be said about CO2 recuperation in parallel with biomass gasification for the production of light olefins? Are there successful cases in Europe avoiding biogenic CO2 emissions? Are there other insights in conversion pathways out of Fischer-Tropsch, like methanol to olefins? I think methanol to olefins is a technology that you can buy off the shelf from the larger EPCs. Successful sequestration of CO2. I'm not completely sure where this is being done, but I know that Shell is building a biofuel plant in Pernis in the Netherlands, where they will capture the CO2 for sequestration, so generating negative emissions. So that's an ongoing activity. And what can be said about the CO2 recuperation in parallel with biomass gasification for the production of light olefins? I'm not completely sure if I understand this question.
Maybe I just add on this. So I think the scarcity in that case is always the hydrogen, right? Where do I get the renewable hydrogen from to have the perfect carbon to hydrogen, let's say, ratio? And well, you can do a lot, but it needs to make sense, more or less, to be very frankly speaking.
Yeah. And then there's at the top a question by Ayush Agarwal. Where do you see hydrothermal processes competing with traditional pyrolysis or gasification, which require dry feedstock to begin with? Personally, I don't see any competition yet. I think it's an emerging field. The technology is, I would say, quite advanced, but not so much deployed that there will be competition anytime soon. So for now, I think we're good with what we have. And then there's a comment by Paolo Castelli, and I think that's also in line with what Johannes just mentioned. In case that nuclear power is is widely available. This would allow, I think, a higher conversion of carbon in many of these cases, and significantly improve the TE analysis. But that's, I think that's for the future. It's something that we need to build a lot more if we want to go there. I think there's no more questions open in the Q&A. Then if there's no more comments or thoughts, final thoughts from the presenters or from the authors of the reports, then I would like at least to thank Johannes Lindorfer and Jitka Rebek for their nice presentations on these reports, which are available, well, for task 42 around summer. For task 33 on our website, you can find the report on implementing gasification in biorefineries or in industrial settings, with the 4 case studies as separate items to be downloaded and reviewed. And you can find the contact details there of all the participants. So if you have questions later on, feel free to contact us directly, and we will be happy to answer any of your remaining questions. Thank you.
Yeah, I may also add as a final note that the recording of this webinar will be available on IEA Bioenergy's website in the webinar section. So if you need to review something about the presentation of the speaker, feel free to check it out on IEA Bioenergy's website.
Okay, thank you. Bye-bye.
Thank you. Bye.
Bye.